Hey everyone, and welcome back. Ready to get a little cosmic? Today we're diving deep into the world of new physics. Yeah, we're talking about the really out there stuff, the ideas that could totally rewrite our understanding of the universe. We'll be pulling from an awesome article called Exploring New Physics, Unraveling Dark Matter, Quantum Gravity, and the Theory of Everything. It's wild stuff, really makes you think.
It sure does. And you hit the nail on the head. We're not just talking about small discoveries here. New physics is all about those big, groundbreaking ideas, the ones that could completely change how we understand how the universe works at the most basic level.
Okay, so it's not like adding a few more pieces to a puzzle. It's like finding out we've been working on the wrong puzzle this whole time.
Exactly. It's all about questioning the core ideas of physics. And one of the best examples of this is dark matter. You've probably heard of it. It's this mysterious stuff that makes up a huge chunk of the universe, something like 27%. But here's the kicker, we can't even see it.
Yeah, that's always blown my mind. It's like trying to study a ghost. So how do physicists even begin to investigate something that's basically invisible?
Well, it all comes down to gravity. We can see dark matter's effects on the things we can see. For instance, galaxies spin way faster than they should based on the stuff we can see in them. This tells us there must be something else there, something massive but invisible, providing the extra gravitational pull to keep these galaxies together.
So it's like we see these stars swirling around way too fast, and that's the clue that there's this hidden structure of dark matter holding it all together.
Exactly. And that's just one part of it. There's also gravitational lensing, where light from faraway galaxies gets bent around massive objects, including ones we can't see. This bending tells us there's way more mass out there than what we can directly observe.
It's amazing how we can figure out that something so fundamental exists just based on its gravity. But not everyone agrees that we need dark matter to explain this, right?
Mhm.
I know our article mentions some other ideas.
That's right. Some physicists think we might be approaching this the wrong way. Instead of saying there's dark matter, maybe we need to rethink how we understand gravity itself. And that's where the concept of modified gravity comes in.
Modified gravity. So we're talking about ditching Einstein and his theory of general relativity. That seems pretty radical.
Not necessarily getting rid of Einstein's work entirely. General relativity has been incredibly successful at explaining gravity on the scale of our solar system. But maybe it needs some adjustments when we're looking at the scale of galaxies or the entire universe.
Okay, so what kind of adjustments are we talking about? How are physicists trying to modify gravity?
There are a few different approaches, but one popular one is called MOND, which stands for Modified Newtonian Dynamics. It basically proposes that gravity acts differently at very low accelerations. And this could explain why galaxies rotate the way they do without needing dark matter.
That's a big if, though. Changing a fundamental part of physics like general relativity seems pretty risky.
It's definitely a bold move, and there's a lot of debate in the physics world about whether modifying gravity is the right way to go. But some observations can be explained really well by these modified gravity theories without needing dark matter. For example, there's a link between how much visible matter there is in galaxies and how fast they rotate. And MOND naturally predicts this link.
So it's like a cosmic tug-of-war right now between the dark matter supporters and those who think we need to update our understanding of gravity.
Precisely. And it's an exciting debate because it could lead us to a much deeper understanding of the laws that govern the universe. But whether it's dark matter or a modified theory of gravity, it's clear that there's something big missing from our current picture of the cosmos.
Yeah, it's wild to think about all these fundamental forces and particles shaping the universe around us that we barely understand. And speaking of fundamental forces, our article talks about this almost legendary search for a theory of everything.
Ah, yes, the holy grail of physics, a grand unified theory, or GUT. It's this ambitious idea that we could unite all the fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, all into one beautiful, elegant, theoretical framework.
So instead of having three different sets of rules for the universe, physicists are looking for that one master rule book that explains everything.
Exactly. It's like finding the cosmic Rosetta Stone, a key to unlocking the deepest secrets of the universe.
But isn't that incredibly hard to achieve? I mean, these forces seem to work on such different scales and with different properties.
It's definitely a huge challenge, but physicists have actually made some progress toward unification. For example, the electroweak theory, which unifies electromagnetism and the weak nuclear force, was a major breakthrough in the 20th century.
So we've already combined two of the forces. But how do you even begin to bring the strong force into that mix?
That's where things get even trickier. The strong force, which holds quarks together inside protons and neutrons, operates at way higher energies and over much smaller distances than the electroweak force. But there are some exciting hints that unification might be possible.
Okay, I'm all ears. What kind of hints?
Well, at super high energies, like those found in the early universe, the strengths of all the different forces seem to converge. It suggests that they might have been unified at some point in the distant
So
past.
that's like tracing the forces back to their origin, back to a time when they were all one single unified force. That's mind-blowing.
It's a really cool idea, and it's one of the main motivators behind the search for a GUT. Because if we could understand how the forces were once unified, it could unlock a whole new level of understanding about the nature of reality.
Okay, so we've covered dark matter, modified gravity, and the search for a grand unified theory. But there's one more piece of the new physics puzzle we haven't talked about: quantum gravity.
Ah, yes, and this might be the toughest challenge of all. It's about merging the world of the very small, which is governed by quantum mechanics, with the world of the very large, governed by general relativity. These two incredibly successful theories, which have revolutionized how we understand physics, seem to clash when we try to put them together.
Yeah, I've heard that quantum mechanics and general relativity just don't get along. It's like two cosmic titans battling it out. But why is it so important to reconcile these two theories?
It's crucial because some things in the universe can only be understood if we combine these two theories. Black holes, for example. These are objects with such strong gravity that they warp space and time in ways general relativity alone can't fully explain. And the very beginning of the universe, the Big Bang, involves such extreme densities and energies that we need both quantum mechanics and general relativity to describe what happened.
So if we want to understand the most extreme parts of the universe, like black holes and the Big Bang, we need a theory of quantum gravity. But our article mentions that there are different approaches to this problem. Can you tell us about some of the leading contenders?
Sure. One of the most famous approaches is string theory. It proposes that the basic building blocks of the universe aren't point-like particles, but tiny vibrating strings. These strings can vibrate at different frequencies, and those vibrations create the different particles and forces we observe.
So the universe is like a giant symphony played on these tiny strings. Does that mean there's a conductor somewhere?
Well, not exactly, but the idea that the universe might be fundamentally musical with all its complexity arising from vibrating strings is definitely an appealing one. And string theory has the potential to unify all the forces of nature and provide a framework for quantum gravity.
Okay, that's string theory. What are some other ideas in this race to unify the quantum world and gravity? Our article also talks about loop quantum gravity.
Right. Loop quantum gravity takes a different approach. Instead of strings, it suggests that space itself is quantized. It's woven from tiny loops that can't be broken down further. These loops interact with each other and with matter, creating gravity and the other forces.
So it's like the universe is built on this fabric of interconnected loops. And these loops are the fundamental building blocks of reality. That's pretty wild.
It is, and it paints a very different picture of the universe compared to string theory. Both string theory and loop quantum gravity are still being developed, and there are many hurdles to overcome. But the search for quantum gravity is one of the most exciting and potentially groundbreaking areas of physics today.
Yeah, it's amazing to think that we might be on the verge of a scientific revolution, a new understanding of the universe that could change everything we thought we knew about reality. But all this talk of dark matter, modified gravity, grand unification, and quantum gravity, it seems very abstract. Is there any part of new physics that has more, well, down-to-earth potential?
You bring up a good point. And that brings us to the quantum measurement problem. Unlike those big cosmic mysteries we've been talking about, this problem is much more tangible, with potential applications in the near future.
Okay, tell me more about this quantum measurement problem.
It's all about the line between the quantum world and the everyday world we experience. Quantum systems have some pretty weird properties, like superposition and entanglement. Superposition is the idea that a quantum particle can exist in multiple states at the same time. And entanglement is when two particles are linked so that they share the same fate no matter how far apart they are. These properties seem to go against common sense, but they've been proven by experiments over and over again. But when we try to measure these quantum systems, they seem to choose one state, like they're collapsing the superposition. The question is, how does this shift from the quantum world to the classical world happen? What makes this collapse occur?
So it's like the quantum world is full of possibilities, but as soon as we look at it, those possibilities collapse into just one outcome, like the universe is playing hide and seek with us.
That's a good way to think about it. And while the philosophical side of this is fascinating, what's really exciting is the possibility for practical applications. By understanding how the quantum world transitions to the classical world, we could build incredibly precise sensors and measurement devices.
So we're talking about technology that could revolutionize how we measure and understand the world around us. What kinds of real-world uses are we talking about?
Think about fields like nuclear fusion research, which depends on a quantum phenomenon called tunneling. A better understanding of quantum measurement could help us improve fusion processes, getting us closer to clean and sustainable energy. Or imagine super-sensitive detectors that could transform medical imaging, environmental monitoring, or even material science.
Okay, so we've gone from the vastness of the universe to the tiny world of quantum measurements. But our cosmic journey isn't over yet.
You got it. And this one might be the biggest mystery of them all. Dark energy.
Dark energy, that sounds ominous. What is it exactly?
Remember how we said dark matter makes up about 27% of the universe? Well, get this. Dark energy makes up a whopping 68% of the universe's total energy, and we have almost no clue what it actually is. What we do know is that dark energy is somehow causing the universe to expand faster and faster.
Wait, so the universe isn't just expanding, it's expanding at an increasing rate. That's a little creepy, right? What does it mean if the universe is not only expanding, but doing so at an accelerated pace?
It's definitely mind-blowing. It means that the very fabric of space-time is stretching at an accelerating rate, pushing galaxies away from each other faster and faster. Imagine baking a loaf of raisin bread. As the bread bakes, the raisins not only move apart, but they also start moving apart faster and faster. That's kind of what's happening with galaxies in our universe because of dark energy.
Okay, so this dark energy is clearly a big deal. But unlike dark matter, which you said could help us understand galaxies, what's the practical use of dark energy? Could we actually harness it?
That's a great question. Unlike dark matter, which might be clustered around galaxies, dark energy seems to be spread evenly throughout space. This makes it super hard to study, let alone think about harnessing.
So it's like this invisible force pushing everything apart, and we're just along for the ride. But if we can't harness it, why is understanding dark energy so important? What secrets might it hold about the universe?
That's the real puzzle, isn't it? Figuring out what dark energy is could answer some of the most fundamental questions about the fate of the universe. Will it expand forever? Will it eventually collapse back on itself in a big crunch? Or could something completely different happen? Understanding dark energy might hold the key to answering these cosmic riddles.
It's incredible to think that something we can barely detect and know so little about could have such a huge effect on the entire universe.
It really shows how much we still have to learn about the cosmos. We're just beginning to understand these fundamental forces and particles that shape everything around us. And that's what makes new physics so exciting. It's a journey into the unknown, a quest to unravel the deepest mysteries of the universe.
It's a journey that challenges us to rethink what we thought we knew and to embrace the strangeness of it all. And on that note, we're going to take a quick break to recharge our cosmic batteries. Join us in part 2 of this deep dive, where we'll explore even more of the mind-blowing world of new physics.
Back again, ready for more.
Definitely. Before the break, we were talking about dark energy and how it's pushing the universe to expand faster and faster. It's kind of freaky to think about what that means for the universe's future.
Yeah, no kidding. It's one of the biggest questions in cosmology today. And the answer really depends on what dark energy is, which is still a huge mystery. Some theories say dark energy is like a cosmological constant, a fixed amount of energy everywhere in space. If that's true, the universe will just keep expanding forever, faster and faster. Eventually, galaxies would be so far apart that they'd be totally isolated from each other. Kind of a lonely picture, huh?
Yeah, a bit bleak. A universe where everything just drifts further and further apart. Are there any other possibilities?
Oh, yeah, for sure. There are other theories where dark energy isn't constant, it changes over time. And that could lead to some very different outcomes. For example, if dark energy gets weaker in the future, the expansion of the universe could slow down. And eventually, gravity might become strong enough to pull everything back together in a big crunch.
So instead of expanding forever, the universe could collapse back in on itself. That's a
Yeah.
pretty dramatic ending.
It is. And there are even weirder possibilities. Some theories suggest dark energy could get so strong that it literally rips apart space-time itself, leading to a big rip where everything from galaxies to atoms is torn to shreds.
Whoa, a big rip. Now that sounds like something straight out of a sci-fi movie. But it seems like we're a long way from knowing which of these scenarios is most likely.
You're right, we need a lot more data, more observations to figure out what dark energy really is and what it means for the future of the universe. That's where all these new telescopes and experiments come in. So exciting.
Speaking of exciting new tools, let's switch gears for a bit and talk about the technology side of new physics. Earlier, we were discussing how quantum measurement could lead to big advances in areas like nuclear fusion. What other technological revolutions could come out of exploring these mind-blowing concepts?
Oh, the possibilities are huge. It's tough to say for sure what the future holds. But one area that's super promising is quantum computing.
Quantum computing. That's been all over the news lately. What makes it so different from the computers we use every day?
So regular computers store information as bits, which can be either a 0 or a 1. But quantum computers use qubits, which can be both 0 and 1 at the same time. It's called superposition. This lets them do certain calculations way faster than classical computers, exponentially faster.
So instead of just two options, 0 or 1, a qubit can be in both states at once. It's like a computer that can explore multiple paths at the same time.
Exactly. And that ability to use quantum stuff like superposition and entanglement opens up a whole new world for solving complex problems that are impossible for regular computers to handle.
Wow, so what kind of problems are we talking about? What are some potential uses for quantum computing?
Oh, the applications are vast. It could revolutionize fields like medicine, materials science, artificial intelligence, even cryptography. For example, quantum computers could simulate how molecules behave, leading to new drugs and materials. They could even be used to crack the codes that protect our online info, which is both exciting and a little scary.
It sounds like quantum computing could be a game changer, both for good and bad. Are there any other technological advancements on the horizon that could come from new physics research?
Another area to watch is new materials based on our understanding of quantum phenomena. For instance, there are things called topological insulators, materials that conduct electricity only on their surface, not inside. This unique property could lead to more efficient electronics and maybe even new types of quantum computers.
So we're talking about materials that defy our normal understanding of how things work. They sound almost magical.
They do, and they show how exploring the quantum world can lead to totally unexpected and potentially world-changing technology.
It's incredible how interconnected it all is, how pursuing abstract theoretical knowledge can result in practical applications that could change our world. But before we get too carried away with the future, I think it's important to think about the ethical side of these advancements too.
Oh, absolutely. That's a crucial point. With any powerful new tech, we need to think about the ethical implications and make sure these advancements benefit humanity as a whole.
Right. We need to have serious conversations about the potential risks and benefits of things like quantum computing and AI. And those discussions need to involve not just scientists and engineers, but also ethicists, policymakers, and the general public.
Totally agree. Science and technology don't exist in a bubble. They're shaped by our values and ethics, and it's on us to ensure that these powerful tools are used wisely and responsibly.
Well said. Now, we've been focusing on the more practical aspects of new physics, but let's not forget the philosophical implications of these discoveries. These ideas are truly mind-bending and challenge your very understanding of what's real.
Definitely. New physics doesn't just change how we see the physical universe, it also changes how we see ourselves and our place in the cosmos. For example, the idea that the universe is expanding at an accelerating rate raises big questions about the nature of time, space, and what it means to exist.
It's a humbling reminder that we're part of something much bigger than ourselves, a universe that's vast, complex, and still mostly unknown.
It is, and that sense of awe and wonder is one of the best parts of studying new physics. It's a journey of discovery that always challenges our assumptions and expands our horizons.
It's a journey that encourages us to embrace the unknown, question the familiar, and marvel at the beauty and complexity of the universe.
Exactly, and who knows what amazing discoveries are waiting for us just beyond what we currently understand.
That's the exciting part. We're always pushing the limits of what we know, and each new breakthrough opens up a whole new world of possibilities.
And I think that sense of wonder, that thirst for knowledge, is what will keep driving us to explore the universe and understand our place within it. New physics isn't just about science, it's about the human spirit, our curiosity, and our desire to make sense of the world around us.
Beautifully put. It's been fantastic exploring the frontiers of new physics with you. And to all our listeners, we hope this deep dive has sparked your curiosity and inspired you to keep exploring the wonders of the cosmos.
Don't forget, the universe is full of mysteries just waiting to be discovered. So keep asking those questions, keep challenging your assumptions, and keep looking up at the stars with a sense of awe and wonder. Who knows what mind-blowing discoveries are just around the corner?
Thanks for joining us on this deep dive. Until next time, keep exploring and keep those aha moments coming. And we're back for our final dive into the world of new physics. We've covered some seriously mind-bending stuff, from the invisible dark matter holding galaxies together to the wild possibilities of quantum gravity.
Yeah, it's been quite a journey. It's amazing how these ideas make you question what reality even is.
Totally. It's not just about equations and labs, it's about pushing the limits of what we can even comprehend about the universe. One thing that's really struck me is just how vast and mysterious it all is.
Absolutely. It's humbling to realize how much we still don't know. We've come a long way in understanding the universe, but each new discovery seems to open up even more questions.
It's like peeling back the layers of a cosmic onion. There's always another layer. And that sense of mystery, that feeling of being on the edge of the unknown, is what makes new physics so fascinating.
It's definitely what keeps scientists going. That drive to explore, to question, to go beyond what we know is what leads to those aha moments.
And sometimes those breakthroughs come from the most unexpected places. We've talked about how new physics could lead to new technologies, but I'm also curious about how these ideas impact other fields, even fields that seem totally unrelated to physics.
That's a great point. Knowledge rarely stays put in one little box. What we learn from new physics can spark new ways of thinking in fields like philosophy, art, even computer science.
So how's new physics influencing these other fields? Can you give us some examples?
Sure. In philosophy, ideas like quantum entanglement and the multiverse are making philosophers rethink what they thought they knew about cause and effect, identity, and the nature of reality itself. Artists are also finding inspiration in the mind-bending images and concepts from new physics, creating art that explores the connections between science, imagination, and how we experience the world.
It's amazing to think that trying to understand the laws of the universe can have such a huge impact on culture and how we think.
It really shows how everything is connected and how powerful ideas can jump between different fields. The sharing of ideas is super important for creativity and innovation in all areas of human endeavor.
So true. It reminds us that science isn't just about facts and figures, it's a way of thinking. It's about being curious, questioning what you think you know, and being open to new perspectives. That's valuable no matter what you're interested in.
Exactly. It's about embracing the unknown, challenging the familiar, and searching for new ways of seeing things. Who knows what incredible discoveries are waiting for us just beyond what we understand now?
That's what's so exciting. We're always pushing the boundaries of knowledge, and each new breakthrough opens up a whole new world of possibilities.
And I truly believe that that sense of wonder, that thirst for knowledge, is what will keep us moving forward in our exploration of the universe and our place within it. New physics is more than just science. It's about the human spirit, our natural curiosity, and our desire to understand the world around us.
It's been an amazing adventure exploring the frontiers of new physics with you. And to everyone listening, we hope this deep dive has sparked your curiosity and inspired you to keep exploring the wonders of the cosmos.
Remember, the universe is full of mysteries waiting to be uncovered. So keep asking questions, keep challenging those assumptions, and keep looking up at the stars with a sense of wonder and awe. Who knows what incredible discoveries lie ahead?
Thanks for joining us on this deep dive. Until next time, keep exploring and keep those aha moments coming.